Hi, I'm Brian Ocorn, and I'm presenting our work, Just Go with the Flow, Self-Supervised Scene Flow Estimation. When interacting with highly dynamic environments, like those found in autonomous driving, it is crucial to track the position and velocity of objects in the scene in order to better predict their future motions. This is traditionally done using a segmentation-based pipeline. The input clouds are segmented into unique objects, and the motion of each object is individually tracked to predict future motion. Unfortunately, if there are errors in segmentation, they will propagate to the tracking algorithm, leading to incorrect estimates of how the object will move, and potentially tragic results. This problem stems from focusing on objects instead of focusing directly on the data. Using SceneFlow, the 3D analog of optical flow, we compute a 3D motion vector for each point in the scene, removing any reliance on object segmentation. Scene flow estimation is a growing area of research, and like many vision problems, deep learned methods have provided the most accurate results. One such method is FlowNet 3D, which uses a point net architecture to achieve state-of-the-art results on real data. These methods, however, require large amounts of labeled data to train, and labeling real point clouds with dense motion annotations is an extremely time-consuming process. We propose a self-supervised training pipeline, which allows us to train on large amounts of unlabeled real data, while avoiding the high cost of human annotation. Given two temporally sequential point clouds, taken at time t and t plus 1, shown in blue and red respectively, we estimate the forward flow of each blue point and project them into the red cloud's time frame, using a nearest neighbor loss to guide this flow estimate. The transform clouds are then projected back to their original time frame using the same flow network, and a cycle consistency loss is applied. For the nearest neighbor loss, we estimate the flow for each point x and project it forward in time. Now if we knew the true flow, we could use the distance between the ground truth projection and our position as supervision. However, this would require annotations, which we would like to avoid. Instead, we use the nearest point in the target cloud as a pseudo-label and minimize this distance. This nearest neighbor loss brings the projected points closer to the surfaces in the target frame. By itself, this loss is not sufficient for learning flow. For example, if all the points are mapped to a single point in the target frame, this would lead to a nearest neighbor distance of 0 and a perfectly optimized loss. To counter this local minima, we force the mapping to be invertible with our cycle consistency loss. Given the projected point cloud produced by our forward flow, we compute the reverse flow for each point back to its original time frame. As each point has a known starting position in this frame, we can use the distance induced by the cycle to further supervise our training. This cycle loss also has a degenerate solution, which is to predict 0 forward and backward flow at all points, leading to 0 loss. This local minima, however, is countered by our nearest neighbor loss. Thus, combining them helps avoid such degeneracies and allows the network to learn the true solution. One problem with the pipeline as described is that it assumes the projected clouds look similar to the real sensor data, when in fact they can be quite noisy. This is particularly harmful when the noisy cloud is used to compute the reverse flow, as the network is intended to compute the flow between two realistic point clouds. To ameliorate this situation, we use the nearest real point to the projected point as an anchor, pulling the points closer to the associated surface. In practice, we find this greatly improves our results. When training scene flow algorithms, the models are commonly pre-trained using a large amount of synthetic data, such as the Flying Things 3D dataset. The resulting model is then fine-tuned on a small amount of annotated data using supervised training. Similarly, we start with the same synthetically pre-trained model. However, our self-supervised training procedure allows us to also pre-train on large unannotated datasets such as new scenes, with additional fine-tuning on the target dataset using self-supervised training. We test our method on the Kitty Scene Flow dataset using the FlowNet 3D network architecture. A model trained on purely synthetic data is able to estimate scene flow with 25% of the predictions falling within 5 centimeters of the ground truth flow. Supervised fine-tuning on a small amount of labeled real data brings this accuracy up to 31%. Our method, using only self-supervised training and a large unlabeled dataset, achieves an accuracy of 46%, with a slight improvement when a small amount of labeled data is added. We see similar trends in the 10 centimeter accuracy, as well as the endpoint error, though the endpoint error does see more improvement with the addition of annotated data. An ablation analysis shows the relative importance of the components of our method in the purely self-supervised case. When the nearest neighbor loss is removed from the system, we see a 30 percentage point drop in performance. Removing the cycle loss results in a 15-point drop, and using nearest neighbor and cycle loss without anchoring reduces the performance by 24 points. And these patterns persist when self-supervised fine-tuning is added. Qualitatively, we find that our method outperforms the baseline on the new scenes dataset. The target cloud is shown in green and the projected cloud in blue. As you can see, we are better able to track the cyclists, outlined in red, when compared to a method trained purely on synthetic data. As new scenes contains no scene flow annotations, supervised fine-tuning is not possible. In this talk, we presented a self-supervised method of learning scene flow estimation that is able to leverage large unannotated datasets and match and exceed the performance of supervised methods which are restricted to smaller labeled datasets. Please read our paper for more in-depth information, and thank you for listening.